So it's time to start for us. Welcome to our Friday's Control seminar. Before I begin, I'd like to acknowledge our sponsors, which is the Toyota and Seagate, I believe. And it's my great pleasure to introduce our today's seminar speaker, Professor Xunyuan Yin. Professor Yin is from Nanyang Technological University in Singapore. He got his PhD degree in 2018 from University of Alberta in Canada. He was a postdoc for a few years, and then since 2021, he's an assistant professor there in School of Chemistry, Chemical Engineering, and Biotechnology. He's an associate editor for Control Engineering Practice, and a member of IEEE Control Society Conference Editorial Board. He's also a member of Journal of Process Control Paper Prize Selection Committee. And it's a great pleasure to introduce his talk, Learning-Based Koopman Modeling for Efficient Estimation and Control of Nonlinear Processes. See you.
And first of all, I would like to thank Professor Ilya Komanovsky for inviting me to give this talk. And I would also like to thank everyone for taking the time to attend today's seminar. Indeed appreciated. And thank you so much for your time. And I would like to take this unique and great opportunity to share some of our recent research progress, to seek your feedback, to seek your expert opinion and comments so that we can further improve on. And so as mentioned by Professor Komanovsky, so I'm from a school of this long name, chemistry, chemical engineering, and biotechnology. So at least this is the longest name I have ever seen. But so I'm from the chemical engineering department. I identify myself as a control engineer. We work on control series, and we also focus on control applications. So our group, including myself, we have benefited a lot from the excellent control research contributed by UMH faculties and researchers. It's no exaggeration, especially the MPC series and applications contributed by Professor Komanovsky, Professor Jingsen, and among many others. Indeed, these areas may look unfamiliar to you, but indeed we have a lot of overlap. We use some of the popular words and terminologies and methodologies, so which were invented by EEE people, by mechanical engineering people, by robotics people. And we have benefited a lot from using such approaches for the more smarter or like a even better operation of some of the industrial processes. And I will begin with introducing some of the details. So first is about the background. We work with those factories. So we focus on the modeling and advanced control of industrial processes, including but not limited to petrochemical processes, biological systems, water systems, among many others. Okay, so these systems have shared something in common. Okay, so basically, theoretically speaking, they are easier to deal with because we do not require such high level of control precision. And these processes are much slower than the robotic system, than the mechanical system, than the electrical system you are controlling. So in this sense, we do not need to consider control implementation at 20, 50, 200 hertz. So that is probably some easy parts for us to handle, but we also face some challenges. These processes have super large scales, and the dynamics have a very high nonlinearity, and we can see very complex structures, and this process also contains highly integrated operating units. And there are several factors we'll need to take into account when we consider process operation. Of course, first priority is given to the operating safety always, right? So we'll like to avoid explosion, we'll like to avoid process shutdown. We'll need to ensure the safety of the personnel and all the equipment and the infrastructure. Okay, and we will also need to take into account the environmental regulations and follow them strictly. And there will be various increasingly strict operational specifications. And at the same time, of course, we'll like to reduce energy consumption. We'll like to reduce greenhouse gas emission. And we'll also like to make the industrial partner happy, which means that we need to help them make some money. So to achieve all these goals simultaneously, It's definitely not easy. And of course, for these large-scale nonlinear processes, nonlinear state estimation and the control problems are always there. We will need to always consider how to address these problems for specific processes carefully and properly and thoroughly and systematically. Okay, so this is a diagram I think so all the audience are familiar with. We need advanced control because it's critical for appropriate, robust, resilient, efficient, economic, and sustainable system operations and real-time production of products. We need control to make decisions, but for the industrial processes, state estimation is not option, right? Because the process at least contains tens or hundreds of state variables and up to thousands. And on one hand, advanced control requires full state feedback, but on the other hand, we do not have sufficient hardware sensors to measure all these state variables. Okay, state estimation also plays an important role to reconstruct the full state picture as needed for implementing full state feedback control. Okay, so in this topic, we will briefly discuss both estimation and control aspects. Okay, so in terms of nonlinear processes, we may deal with ordinary differential equations. We may deal with dynamic algebraic equations, or we may deal with nonlinear partial differential equations. So we can see this ODE nonlinear system, for example. Okay, and for chemical process engineer, at least from a theoretical point of view, nonlinear model predictive control is a natural choice. And I believe most of you are familiar with these two illustrative graphs. Okay, so MPC looks like forecasts what will be happening in the future. It considers a fixed size control horizon, and by solving optimization, it generates the most appropriate control actions for the future time window. And only the first one will be applied to the industrial system for closed loop implementation of nonlinear MPC. And as we can see the nonlinear system, and if we use nonlinear system model, the model will be used in a straightforward manner as the model constraint. Another advantage of nonlinear MPC, as you all know, that we are able to address the constraints in a straightforward manner because they can be incorporated directly into the optimization. Okay, as I have mentioned, this is a natural choice for the control of many of nonlinear processes, but only from a theoretical perspective. Okay, I will elaborate on this point later on. And with MPC, we can predict what will be happening in the future, and through solving optimization, we generate control actions accordingly. And another advantage is something we have discussed. We are able to handle various constraints on states and control inputs. But for our processes, it has been challenging to construct the nonlinear models because of the scale, because of the complex structure, because of the excessively large number of state variables. And the online implementation, although our process has slow dynamics, the transit time could be minutes, could be hours, or could be even days. But online implementation is still a problem because we cannot change the computing unit for those factories. They're still using SCADA system or district control system offered by, for example, Honeywell, Amazon, ABB, so which were there 20 years ago. So computing power has been limited. They have the money to replace them, but they cannot replace them because of reliability issue or concerns. Okay, so we will need to accelerate the optimization for this nonlinear MPC. This is yet another issue. Okay, another problem, which is a dual problem of a model predictive control. This is a nonlinear moving horizon estimation. So we can see that almost the same system model, but moving horizon estimation aims to address state estimation problem. It's a dual problem of control. Instead of forecasting what will be happening in the future, moving horizon estimation looks back. It reconstructs the state information based on the state measurements within this historical time window. And if we would like to solve the estimation problem, so we'll be applying the first element. So I mean the last element of this estimation window as the optimal estimate of the current system state. Of course, such information within this window will be helpful if we are addressing some smoothing problem. Okay. And similar to MPC, model is used as a constraint. And in addition to that, we are able to impose constraints on the estimates of the disturbances and estimates of the system states. This is quite useful because in process control industry, for example, we understand the pressure stays between 10 bar and 20 bars. We know the temperature of this room must stay between 18 degrees Celsius to 30. I'm sorry, I should use Fahrenheit, right? So probably 70 to 85. 80 is too high, right? 85 is too high. 70 to 80, right? So we know it must be bounded within this region, right? So the estimate should comply with such constraint as well, right? So constraint estimation is also essential for process industry. Okay, but we highlight some of the challenges or limitations of the existing nonlinear MPC and MHC solutions, which means the methods developed based on nonlinear first principle models. Okay, state estimation and control, of course, needs a good dynamic model, right? But for the processes we are considering, the availability of a first principle model, especially an accurate, high-fidelity first principle model, indeed is an issue from a practical point of view, right? For those large processes, it may take years to build a model. It could be costly, it could be labor intensive. And we are also dealing with many uncertainties. For example, we consider a carbon capture plant attached to a power plant. The flue gas received from the power plant fluctuates significantly. So these are some uncertainties because we don't know the amount of flue gas we'll be receiving next second until we receive it. These are some external disturbances. When we consider industrial wastewater treatment, the amount of wastewater we receive from the upstream and the composition and the concentration of the materials are also something we cannot predict. These create some additional external uncertainties and disturbances, and which pose limit to the application of the current nonlinear MPC and MHC solutions. And for some even complicated processes, it's just simply infeasible to build a first principle model. It's not an option, okay? And another is about the nonlinearity of a first principle model. Because if we choose to use physical knowledge, it must be nonlinear. So based on the thermodynamics, based on the mass energy balances, it will be nonlinear for sure. But this will pose limitation to efficient implementation of the optimization because of the non-convexity. Okay, so based on this consideration, so we would like to opt out for the first principle modeling, and indeed, it is favorable to try to leverage linear models to account for the dynamics of nonlinear processes, right? So this is the motivation. So we would like to build efficient MPC and MHC designs without performing first principle modeling. Okay, so this is the idea. We have nonlinear process dynamics, but we would like to build a linear model. And the only difference, another difference here between the two models is that instead of using the original state vector, which takes physical meaning, we probably will need to create a new state vector, in a new latent space, because nonlinearity is not eliminated. We are not building a linear model based on Taylor series expansion. It's not a local linear model. It's a global linear model, right? So then nonlinearity will not be gone. So it will be accounted for by another component, which will be a bridge between X and Z, right? So if we are to embrace this idea, so Koopman operator is one of the promising tools. Okay, so Koopman theory was not new. It was proposed about over 90 years ago. And at the very beginning, it established the foundation for finding exact linear representation globally for almost any nonlinear systems. And then later on, people have leveraged this framework and leveraged this concept to build finite dimensional approximated Koopman models for the nonlinear systems. And we will elaborate on this point. And because of the beauty of the Koopman model, the simple structure, right, brings some advantages to control and estimation design and implementation. Because it's a linear, we are able to leverage linear control theory and the technique to address nonlinear control and estimation problems. And here we can see in the past 6-7 years, some Koopman MPC series algorithms and applications have been made available. So including deterministic Koopman MPC, considering the Koopman, a perfect Koopman model, right? a Lyapunov-based MPC and a robust and tube MPC, as well as offset MPC, so which leverages common filter to estimate the system disturbances or model mismatch. And we have also witnessed wide applications of a Koopman-based MPC across different areas, including software robots. I believe Dr. Bruder is with UMH as well, right? And the power grid system, molecular systems, and chemical and biological processes. Okay. A recap of the equation. Now we can see the autonomous system. According to Koopman theory, so this is very straightforward. According to Koopman theory, for any autonomous nonlinear system, there always exists a nonlinear mapping from G to, this should be Z, sorry for the typo. There always exists such a nonlinear mapping, but dimension is not deterministic. It's something we need to explore. There always exists such a nonlinear mapping such that the observables in the latent space or in the lifted space will be governed by a matrix K. This is the Koopman operator. In this way, we govern the dynamics of the nonlinear system in a lifted space in a linear manner. Okay, but the problem now arises. So how do we establish this K matrix? And more importantly, how do we account for the nonlinear mapping? So here denoted by G. Okay, these are two problems that need to be solved. Okay, and before going through the solutions, so here we have a tall example, which is not tailored by us. And this is so far the only numerical example I have ever came across that can be used to illustrate an exact Koopman operator can be identified or can be found. Okay, we can see the two-dimensional ODEs. First one is linear, the second is nonlinear. And we can find such a nonlinear mapping, right? So we increase the dimension of state vector from 2 to 3. In this lifted space, we are able to build 3 new ODEs, right? And Z1, Z2, Z3 dots have dependence on the 3 new observables in a linear manner. And now we are able to formulate a Koopman matrix. This is the Koopman matrix. And this solves the problem perfectly. We find the Koopman operator, we find the nonlinear mapping. But this is the only example that has been solved perfectly, right? Okay, so let's take another look at this equation. And I move this 2 to x2. Let's see what will happen. There'll be endless search of the lifting function. And we may still be able to find a Koopman operator, but that will be infinite dimensional. And we are still lucky here because we can find the nonlinear mapping to find the exact Koopman operator, although it is infinite dimensional. For some other nonlinear processes, so we can now even identify which direction should we go toward in order to find the nonlinear mapping. But even for this case, it's useless for control, right? Because we will need to design a scalable control system. We cannot define and design MPC and MHC based on an infinite dimensional linear state model. So we would rather work on the nonlinear model directly. Okay, and based on these considerations, people have considered this avenue. How about we leverage the global linearization concept, but we find an approximation of the Koopman operator. We do not need to find the exact Koopman operator. As long as the Koopman operator can represent the nonlinear dynamics of the process up to, say, like 97, 98% of accuracy, we are okay, we are good, right? Because we have robust MPC solutions for linear systems, right? Based on these considerations, multiple approximation methods have been proposed. So one is the dynamic mode decomposition, but that is overly simple. So this is beautiful because it's we can see it's also published in Journal of Fluid Mechanics. And but based on this dynamic mode decomposition, an even more popular method has been proposed: extended dynamic mode decomposition. Okay, so I will go through this method first before I introduce the learning-based approaches. Okay, so I would like to use 2 case studies to illustrate how extended dynamic mode decomposition can be leveraged to build a Koopman model, to build an approximation of the Koopman model in a finite dimensional state space, although we have a dimension increase, right? We can see that, again, this nonlinear process because we use this Koopman operator for state estimation. So we also introduce the disturbance and the environment noise, but that doesn't matter too much. Okay, our idea is to build a linear deterministic Koopman model. This could be stochastic, but we just use deterministic model structure for easier illustration. Okay, and this is the measurement, and this is a reconstructed system state. Again, there will be a nonlinear bridge between X and Z. But when we would like to recover the X, we would prefer to use a linear matrix. This is something we might identify, or this is something we may be able to construct. So based on ad hoc selection of the lifting function, and I will also elaborate on this point. Okay, so this is the idea like from a paper published in 2018. This is an automatic paper. Okay, in this paper, so Koopman approximation has been considered for the first time for controlled system. This is no longer an autonomous system. This is a controlled system, and the idea is to build this linear Koopman matrix. Again, problems less in how to find this G matrix. I'm sorry, this lifting function vector as well as the AB matrices. And with this Koopman model, we are able to apply H infinity control, LQR, and linear MPC. Okay. So the idea is straightforward. Augmented, so this is with a bit abuse of notation. Augmented state vector is constructed. So the input, control input is appended to the state vector. And this is the dynamics of the nonlinear system, nonlinear dynamics. And the idea is to find the Koopman operator under the lifting function for the lifted state vector. And in this way, we do not want to find the exact Koopman operator. Instead, we are going to find a finite dimensional approximation of the Koopman operator, which is denoted by kappa tilde. And this is something we do not find from a theoretical point of view. So we could do manual selection, and we do trial and error analysis to find probably or most appropriate set of lifting functions. Okay, and remember that in the augmented vector, we have future input and the future state. But fortunately, we only need to predict the future state. We do not need to predict the future input. So we do not need to take into account the second row or the second block row of this whole vector. Because when we build a Koopman model, we like to minimize the prediction error. So we like to minimize the error between this is Z k plus 1 minus k times zk. Right? So we like to minimize the one step ahead prediction error according to extended mode decomposition, right? And again, this X incorporates both state and input, but we only need to predict the future state. So these two step blocks can be disregarded. And this will simplify the least square problem to this expression, right? With this expression, this is a linear least square problem, although we have the nonlinear lifting function, right? So phi is something we can specify, and we have the X data, and we have data here, we have data here. So A, B are the only degenerate variables we would solve. But they are linear, so this is a linear least square. So we have the closed form expression to the for the solution to this least square problem. And we solve for A and B, and C and D can be formulated as two other least square problems. But based on specific selection of the observable function, C and D can be determined in a straightforward manner. Okay, so based on the Koopman model, we can formulate, of course, linear moving horizon estimation scheme or linear MPC. I'll just skip the details. And I will use an idea to illustrate how Koopman operator is applied here. Right, so Koopman theory is applied here. We can see the 4 interconnected temporal actors. So we do not need to consider too much about the background information. Here, the concentrations are the material concentrations in the 4 tanks, the product concentrations, and the temperatures. If you can see the state estimation, only temperatures can be measured online using sensors. And we'll like to use state estimation to estimate the concentrations in the 4 tanks. We can collect data for the concentrations offline, but we cannot do it online. We can use lab analyzer, get a sample, we send back to the lab. It can take 30 minutes to 2 hours, depending on the nature of the substances we're analyzing. But online measurement is not possible, but we can measure the temperatures always. So the idea here is to use temperature measurement to reconstruct all the system states, especially the concentrations in the 4 reactors. Okay, And this is the manual selection of the observable function or the lifting function. Quite straightforward. Original system state, because this makes the estimation easier. So when we reconstruct X, the D matrix can be determined as identity matrix plus some zero, right? We do not need to solve the least square for D in this case. And then we add X squared and e to the power X. Okay. And with this selection, we solve the least square problem. Least square is not an optimization problem. We have the analytical solution to it. And here is the modeling performance. And I would like to mention that this is an infinite step ahead prediction of the model error. We never updated the model prediction using any state feedback. So this is, I think, two reasons. So most critical reason is that this system is open loop stable. And we have identified a stable AA matrices for this process. I think that's why we can realize infinite step ahead prediction. And when we further incorporate the sensor measurements for state estimation, because state estimation takes into account additional information from online measurements of the temperatures, it makes sense that estimates are even more accurate than open loop prediction, right? But the estimation is not the emphasis. The emphasis on is about how we build a linear model to represent the nonlinear dynamics to facilitate design and the implementation of linear estimation scheme. And we have also conducted experiments. This is a facility from Professor Bill Huang's group at Alberta. And we can see the water levels in the 4 tanks. And we selected the same lifting function. And it worked well again for this process, for the same set of lifting functions. And here is the open loop prediction for all the system states. So we can see the bias is more significant as compared to the chemical process because this is a real but noisy data. But still the results are good in the sense that if we further implement test state estimation, we can see that estimates for all the system states are more accurate. Because here that I would like to emphasize, for all the 4 system states, in terms of water levels in the 4 tanks, we can measure online for sure. But we just use 2 of them as the feedback information to the state estimator, and we reconstruct all the 4 system states only to test the performance of the whole algorithm. Okay, so far it looks so good, but we are still motivated to work on automatic selection of the lifting functions, the G function. I will explain why. We consider the same process. And this is the set of lifting functions we have considered in the previous chapter. So far, so good. Let's see. We further add in another element. So we still keep the original 3, but we just added in 1 more. And this does not look crazy or ridiculous, but this decreases the prediction performance significantly. And the state estimator diverges. Honestly, we don't know why, but we tested some other candidates. It even worsened the prediction result. So this was the original motivation for us to consider how to address the lifting function selection in a more systematic way, right? Okay, so next chapter, how we address automatic lifting function selection. Okay, this is, I will go through this very quickly. This is not yet the automatic selection, and we call it a semi-automatic selection of the lifting function. And we propose an algorithm based on the sparse identification of nonlinear dynamics. People call it Cindy algorithm. And we integrate common filtering with Cindy algorithm to estimate. So first, I would like to explain the idea because I think the font size is too small here. It will be hard for you to understand the details. I will just briefly explain the idea. We create a rich library which contains candidate lifting functions. Could be different types of monomials, different types of polynomials, some exponential functions, or some rational functions, right? So it could be a very rich library which contains 500, 600 candidate functions. We can even enrich it, no problem, up to 1,000, 2,000, even 2,000 is fine, but we do not have so much knowledge to create a so big library. The idea here is that we leverage, we first integrate common filtering with Cindy idea, and we assign a random parameter to each of the candidate functions. So these are the candidate functions, AB, B square, B cubic. And these are the coefficients for these candidate lifting functions. We use common filtering to recursively update these parameters. And we estimate this omega matrix, and we only select the elements after, for example, using 500, 600, or 1,000 samples. We fix this omega matrix. Then we only take out the coefficients that have a relatively large values in terms of absolute values. And for some sparse elements, we just disregard them. Then we find the corresponding lifting function in the library, and we take them out, and this algorithm works so well. So in the following, we also consider reduce all the modeling, but that will be, I would call it quite trivial. We use the proper orthogonal decomposition. So I will just skip the details. And based on this model, because the model accuracy has been much improved because of the use of automatic selection of the lifting functions, the MPC and both the model prediction performance and the MPC set point tracking performance have been much enhanced as compared to manual selection. Okay, and the computation time, of course, this is so we did not list the nonlinear MPC computation time because it's not a fair comparison. Right? We are solving QP problem, not a non-convex problem. And later on, we move towards the automatic selection. I'm sorry for that. So far, we considered how to manually select the lifting functions. And we introduced one practical, simple but practical method to semi-automatically select the lifting function in the sense that we can automatically select lifting function, but we will need to manually create a library. And now we will to automate the selection of the lifting function. So one initial idea is just to use neural network to replace the G. We do not want to use parametric lifting function anymore. We just use a neural network to replace G. That is the idea for the upcoming works. Okay, so first, we consider a time delay system because time delay system is also common in chemical processes. Because when we take a sample, we send back to the lab. Once we get the measurement, it takes at least half an hour. This is a time delay. And this is also a transportation lag. When we transfer material from a distillation column to a reactor, and then we send it to another, for example, heat exchanger or reactor. So it will take quite a long distance and long time to travel. And this also creates some time delays. And communication delay, sometimes it exists, but it's not so significant in process industry. Okay, so here are some factors that motivate us to consider time delay system. And another is about the disturbance and noise. So far, we have seen the establishment of a deterministic Koopman model. We have AX plus BU and plus nothing, right? Because when we leverage the Koopman operator or Koopman modeling framework, especially when we solve the least square problem using extended dynamic mode decomposition, we can only get A and B. How do we account for the stochasticity or the mismatch between the Koopman model and the original nonlinear noisy process, right? So here we leverage a framework called probabilistic Koopman modeling framework. And we consider a general nonlinear system, but the current system state may have dependence not only on the previous one, but also on some historical system states. And here is the illustration of the idea. Okay, so I will explain this idea, try my best to explain this clearly. So here, this is the lifting function, because my apology for use inconsistent notation here. So in different papers, so we'll improve this point. And this is the G function. This is the lifting function. This is X, this is Z. It's X, this is Z. But in addition to that, we would like to make our Koopman model a stochastic one. So we further incorporate disturbance to the Koopman model. So we also use another neural network. Although we display one here, there are two neural networks. The other neural network is to infer the mean and the variance of the disturbance of the Koopman model. So in this way, we update the standard deviation and update the mean value of the disturbance so that we are able to build a stochastic Koopman model. So which means that this framework is quite general. If we do not deal with time delay system, we just simplify the structure. So the main idea here is that we use neural network to account for the lifting function selection. We automate it. The other idea is that we incorporate probabilistic thinking to make the Koopman model a stochastic Koopman model. Right? So we do not only infer the lifted state vector, but we also infer the stochastic information. Okay, and here is the key idea. we take advantage of the state and known input information within a fixed time window. The size of the window may vary, right? So this main idea is to account for the time delays, the dependence on the previous system state, right? So if there's no time delay, we can just remove these building blocks. We just keep this one, right? So we extract the information, the cell state from previous system states and encode. And eventually, we have two neural networks. We use X, U, and encoded state from LSTM to infer future system state in the lifted space, as well as the disturbance. Okay, and this is a Koopman model structure. And there are different versions to update this Koopman model structure. Probably we can put a disturbance term here, but we choose to add in stochasticity when we initialize the Koopman model within each prediction step, because our Koopman model does not only predict the next sample instant state. We will need to provide a good predictability for the entire control horizon. So if n is 10, then our model should be able to provide fairly good prediction for the next 10 steps, right? So for some applications, if control horizon or prediction horizon for MPC is chosen to be 20, then the model needs to be able to predict the future states for the next 20 or 10 sampling instants or sampling periods. And this is the optimization formulated for Koopman modeling. And the theta is the parameter of the neural networks, and ABC are the Koopman matrices. Sometimes this may be reduced to theta A and B. Okay, and the design of MPC will be straightforward once we have the model. We can leverage linear robust MPC design, linear tube MPC design, proposed by UMich researchers. And we have proven the boundiness of the model error, as well as the stability of the Koopman MPC. So in terms of the proof of the Koopman MPC, because we leverage linear theory, so that was not difficult for us. And we did not claim that we made a significant contribution to that. We leveraged some of the excellent work contributed by researchers in the field. Okay, and we have used several applications to illustrate the effectiveness. Of course, there will be some model mismatch, because there's a model mismatch, and further incorporating robust MPC will mitigate this mismatch, but that will not be fully eliminated. But this is something we would like to further explore. Another idea I would like to share is about the economic Koopman model predictive control. And we realize convex optimization for economic model predictive control based on the framework of Koopman modeling. And I would like to explain the idea. So economic model predictive control is an integration of real-time optimization, meaning that optimization of the set points and the real-time set point tracking MPC. So it integrates two levels of optimization and control objectives together. So economic model predictive control is indeed essential for our process industry. So let's consider the desalination process. So current practice is that it will consume 3.5 kilowatt per hour when we process 1 cubic meter seawater. And the government's target is to reduce this number from 3.5 to 2. Two reasons. One is that so people will still need to make some improvements on the hollow fiber membrane used to process the seawater. Another is that for desalination process operation, believe it or not, they use either PID or they use open loop control. Okay, so we expect that there is a huge room for us to help them, right? So we can help them by contributing control solutions and modeling solutions to reduce this energy consumption at least by 10 to 15%. And economic model predictive control may be a good choice. And model predictive control has been applied in across different areas, including Professor Komnowski's work and Professor Sun's work. And so here's the idea. For example, we use a wastewater treatment plant for illustration. Actually, there's no set point to track. When we perform set point tracking, we solve a static optimization problem. But that optimization problem is not valid because we have constantly fluctuating disturbances from the upstream user. There's no optimal set point for this plant, and it doesn't make sense. And from the government and the water agency point of view, they would like to improve the effluent quality, and they would like to lower the overall operating cost. So we put a sum here because we flip the sign for one of them, right? So now we're going to minimize EQ and OCI in order to improve the effluent quality and to reduce the overall operating cost. Okay, so economic model control is a natural solution for this type of problem. Okay, actually, economic MPC for this process is not a new problem, right? So the first paper was published 9 years ago. Nonlinear dynamic model is directly used. Here, U is no input, D is the disturbance. So D contains known disturbance and unknown disturbances. And this is a straightforward formulation, but this is highly non-convex. Model is nonlinear, and the objective function is also highly nonlinear. It has dependence on 23 state variables. And for this process, it contains 145 state variables. And to solve optimization one time using IP-opt in Python, if the control horizon is 15, it takes 5 to 10 minutes. So providing that you have provided a good intro guess. Okay, and more importantly, so time is not the biggest concern. It's a concern, but not the biggest. The concern is that the solution is just comparable to set point tracking MPC. So we just believe that it converges to a local optimum. We are not experts on optimization, but it's just our guess. Okay, and based on these considerations, and again, so that is based on the assumption that the first principle model is already available. 145 state variables, 145 nonlinear ODEs. So how are we supposed to construct it for a real plant? Another issue. Okay, this is the idea. We use a linear model to forecast the future information. Now we have a linear model, one step closer towards convex optimization, but not enough. Cost is still non-convex. The economic cost is nonlinear. How about we use a quadratic cost to approximate the nonlinear cost expression in the original coordinate? Now we have the flexibility to lift the state vector. And how about we just use this lifting function and we construct a quadratic objective function, right? So C hat will be an approximation of the economic cost in the original system state, in the original state space, right? Again, we use a quadratic expression in a higher dimensional space to approximate the economic cost in the original system state, state space, I'm sorry, right? And this is the general idea. And here we penalize the prediction error for the economic cost. And we penalize the difference between the predicted state and the ground truth state. This is the ground truth state, and this is the prediction in the lifted space. So this basically is the output of the G function or the G neural network, right? This is a lifted space. We have a linear model, and we penalize the difference between the predicted cost and the ground truth of the cost. And eventually, we're able to formulate a quadratic optimization problem for economic model control objective. Okay, so here we can further incorporate state constraints, but we have not done this in this work because we would like to deliver a simple solution. This is we call it input-output Koopman modeling and the economic MPC solution. The main advantage is that we use a data-driven method. We do not require first principle model to address economic MPC, and in addition to that, we convert a highly nonlinear optimization problem into a convex formulation. Of course, it's an approximated solution. And we have seen a drastic decrease in the computation time, and effluent quality has indeed improved as compared to the case when we use a 100% accurate nonlinear model and the resulting eMPC. So this probably justifies our hypothesis. So the use of a nonlinear model and the use of a nonlinear cost function will not perform well because optimization has not been solved very well at least using IP-opt. Okay, and here are some simulation results. We have seen significant improvements, and we further extended this idea to address a problem in a more systematic way. And this is a grant-oriented project or research topic. This is a deep learning-based Koopman modeling and economic MPC of shapeboard carbon capture process. So I will just go through the detail very quickly. And this is the whole plant. This plant contains 103 state variables. And here are the diesel engines from the ship. And this is a carbon capture plant, which is used to make the flue gas cleaner. So we will take out 60 to 80% of the CO2 from the emission of the diesel engines of the ships. Okay, and we further extended this idea. So basically, because there are fluctuations, so probably constant B matrices and the D matrices may not be sufficient. So we would like to give some flexibility to the values of the Koopman matrices. And in addition to that, we are going to handle state constraints. Because for this plant, the temperature in one of the columns will be very high to facilitate the desorption of the CO2 from solvent. But the temperature should not be too high. Temperature should always stay below 145 degrees Celsius. My apology for not being able to convert it into Fahrenheit. Yeah, but 145 is the hard constraint, so that we will need to impose constraints on our MPC scheme. So that's why we here not only to predict the cost, but we also predict some of the safety critical state constraints. And we have largely improved this framework so that we are able to address the fluctuations in the disturbances. Here you see that, we can see that the B matrices and the D matrices are actually output by additional neural networks. So we train more neural networks to output the system matrices. Now we do not only train the neural network parameter itself, but we also train neural networks to update the Koopman operators in real time based on the new data we receive. Okay, and again, so we'll only show the best control results here, but it indeed perform well. It is quite robust under different circumstances for this type of plant. And we have also tried it out on some other nonlinear processes. That's why we can confidently showcase the results. Another idea is the meta-adaptive Koopman operator. And this is a more theoretical research and which was submitted to Automatica. And we can see this case scenario. Systems have multiple operating conditions. Similar to our water treatment plant. We have a rainy weather, we have sunny weather, we have a stormy and windy weather, all types of disturbances and all types of uncertain parameters in the system, right? So F has dependence not only on state and input, but also on different parameters, and this parameter may vary. And we can see that the parametric uncertainties, how we deal with the system. Okay, if we say we have 3 operating conditions, we can build 3 sets of Koopman operators. We can build 3 Koopman models, and we make it a switching system. It's one option. How about there are some unforeseen operating conditions, right? So there will be some new extreme weather conditions we have never encountered before, because we consider some of the open water systems, right? So do we build one new Koopman operator? How about you encounter the 5th case scenario, right? So now we're going to build one single Koopman model, which is adaptive and robust to the existing operating conditions, as well as to some new operating conditions. And we leverage the idea of meta-learning. Meta-learning is about the learn or train itself to get the ability to learn and adapt to new environment, right? So for example, one person knows how to hack, how to ski, and how to do cycling, and how to do jogging and walking. And one day, because I'm quite good at these sports, I can learn how to skate very quickly. And this is the idea of meta-learning. Basically, if we translate it into process control knowledge or like a terminology, and I can handle the first operating condition well, I can handle the second operating condition well. When I face a new unforeseen circumstance, I just use a few new data points to adapt to this new environment very quickly, instead of performing neural network retraining. Because remember, we have used the neural network heavily to account for the nonlinear mapping, to account for the generation of the Koopman matrices. So we cannot afford to retrain these neural networks when we face a new operating condition, right? So it's okay to take very long time to train the neural networks offline. But once we move to online implementation, we cannot afford the retraining of the neural networks. We would like to leverage meta-learning to adapt to the new environment very efficiently and quickly using very limited data, right? So for example, when I do scaling, I do not need to attend many lessons, right? So I can just benefit from my experience about skiing last year, right? This is the idea. And I will skip the details, but for different working conditions, say, now we have data from 3 working conditions. Could be rainy condition, stormy condition, and a sunny condition, or probably like jogging, running, and hiking, right? And we build 3 sets of Koopman operators at the very beginning, but we put them together according to the idea of meta-learning. We take the weighted average of all the Koopman operators. We generate 1 single set of Koopman operators. We only have 1 set of ABC matrices. We have 1 single model for all the operating conditions. Too good to be true, right? I agree with you. But we have the adaptation step. So we update this Koopman matrix a little bit once we face a new operating condition. And this matrix will never be perfect, but it will be fairly accurate, it will be fairly robust, and there will be enough for our process control. Okay, and we have made some assumptions. I'm not so sure I can call them like mild or strong assumptions. And the state prediction error can be made asymptotically stable, but in this case, assumption should be very strong. And in addition to that, we also analyze the stability of the closed loop control. I will skip the details. And here are some quick illustrations. So that's why we benefit a lot from across different areas, from mechanical, from robotics. We also use color to illustrate some of our ideas. And of course, we use biological systems and chemical processes to illustrate the ideas and effectiveness and superiority. This is about the, I'm not sure if I have another.
Maybe a couple of minutes.
A couple of minutes. Yeah, I will skip this very quickly. This is another idea. I will just elaborate our main contribution because our systems are largely open loop stable systems. And as we have incorporated machine learning into Koopman modeling, we have the flexibility to specify the property of the AB matrices. Right? So how about we just enforce the Koopman modeling in a way that the Koopman operator is inherently stable, right? So this is what we have done here. We must have a asymptotically stable A matrix because we know that we will be applying it to an open loop stable process. Why don't we just simply make it stable, right? And we enable this through the use of machine learning. And we have also designed a new robust moving horizon estimation design based on the Koopman model for nonlinear processes. And we have analyzed the state prediction error as well as the state estimation error. And we are in the process of applying these algorithms to lab setups. One is the membrane-based biological reactor for water treatment. And this is something we are working on. We will need 1 more tech to finalize the design, and we'll start experiments from next month. And the idea, again, this is a super dirty water. We cannot see the membranes through. We cannot see through, so we cannot see the membranes. But there are many, many hollow fiber membranes which are used to process the water, to generate clean water from the wastewater. And this is a super energy intensive. And we are applying the economic control to minimize energy consumption, while to ensure the quality and the amount of treated water produced from being produced from this facility. And this is about the lab setup of the carbon capture plant. And we worked with Yokogawa on a control system, which is unfortunately not covered by this picture. And we work with the maritime company. The idea here, we have set point here. So we will be trying to build a data-driven model for this plant, and we will test the MPC and economic MPC algorithms. And we have generated some results for this plant, but they do not look good, so I do not put them in this slide. Lab experiment is not easy for us, honestly speaking. And probably I will just stop here. I would like to share something about DPC, and I'll just elaborate on this idea. So DPC, so for Koopman modeling, we still need a full state information, right? Of course, when we recover the full state, we can use the estimation, but for offline modeling, we still need a full picture of all the system states. We need to collect offline data for all the state variables. We have no option. But for example, in the case when even offline data collection may be a problem for certain states, we may probably prefer to use input-output control framework. And this is something that can be addressed by DPC. I would say DPC is complementary to Koopman modeling and the MPC, at least for our process control engineers. And the DPC idea is quite straightforward. It does not use the parametric linear time invariant system model or linear time varying system model. And it uses a non-parametric representation. It only uses input and output data. This is a Hankel matrix. This is about the historical data we collected offline, but we only need U and Y data. U is known input and Y is the known output. So only the sensor data. So whatever we have, whatever we control, we must have sensors. And whatever we already have sensors, we measure them. So data collection is no longer a problem, even for offline data collection, right? So whatever sensor we have, we just leverage the information. And this is so for DPC, this is the formulation of DPC. So people will like to optimize the future input and future output, as well as this GK. So nobody has defined the name of this vector. This is a very tall vector. And probably we can call this a DPC operator vector. This optimization, of course, for linear system, at least this is a convex. But interestingly, as I collaborated with Professor Zhaojian Li from MSU, as we increase the size of the Hankel matrix, the optimization is also very expensive. Okay, this is something we cannot afford, even for our lab setup. Because for the carbon capture plant, we need to generate control action after every 10 seconds to adjust one of the flow rates. Okay, so DPC, even it's a convex optimization, we cannot afford optimization. And so based on this idea, based on this consideration, we incorporate neural network into DPC. The idea is that, so for the G matrix, we use to solve the convex optimization, but now we're going to train a neural network to output this G vector. Okay, very simple idea. But we tested it. It's still not explainable, but we are able to train a DPC, train a neural network to output a vector for DPC without solving any online optimization using, so we were able to do it using only 500 to 1,000 samples, which means that lab experiments or experiments on pilot scale plant have been made possible if we choose to embrace this type of solutions. And we have also extended this for economic model predictive control. And probably it's time for me to stop.
You want to just maybe have last slide to conclude?
Yeah, for sure. And this is about the extension to economic MPC. And I will also like to take this opportunity to thank my advisors. And a special thanks to Professor Ilya Komnowski. So not only for inviting me for this seminar, but also for all the guidance and the support and the mentoring and the invaluable, I would say, suggestions and the encouragement throughout the past years. It was not difficult for me during pandemic, but yeah, I'm deeply grateful to you. And I will also like to thank my colleagues and group members. Without them and without the financial support from the funding agency, we will not be able to generate such results. And thank you so much. And I'll be happy to take any questions.
The floor is open for questions, maybe. Please.
Thank you for the great talk. My question is that when you train your deep Koopman operators, I think for chemical reactions, the model is not control affine, and you cannot decouple the state and the control input, right? So I wonder if you use closed loop data with control, do you have problem with domain shift or the distribution shift when you?
I didn't get your first question. You mentioned that it's not input affine system, right?
Right.
Which means that it's a nonlinear system.
Right. The state and the control input are coupled. So that means if you train your models with some input and you apply to the again, and the input will change. So I mean,
I didn't introduce our treatment.
Yeah.
We did not directly use the sensor method. We leverage the Koopman thinking again. we have performed a nonlinear lifting to address the nonlinearity of the processes.
Okay.
So we do not use Y. We lift Y, and we can further lift U.
Also, it doesn't matter if they are coupled.
Yes, exactly.
Okay.
Exactly.
thanks.
But there's still a lack of theoretical, like rigorous theoretical proof, and we will for sure be working on that. This is the idea. So we think it should work, and it worked. But why it worked and how it works. So this is something we will need to answer.
Okay, thank you.
Any other questions?
Yes, please.
Maybe a quick question. So in the ingredients, there were many different things. So you had nonlinearity, time delays. You also had stochasticity in your system.
Yes.
So in your opinion, in these applications, which one are most important? So, or can you rank them? What do you think is most crucial to address?
Okay. So when we test, it's indeed a good question. And so in terms of the challenges we have been facing, I would say initially it was nonlinearity because we tried out different methods to specify the lifting function, right? So we guessed that. So the bad performance originated from the strong nonlinearity of different systems. But now with machine learning, indeed, if we have sufficient data for training, we are able to build good Koopman models for almost all the processes, including chemical processes, biological processes, water system, and so on and so forth. But now I will say the uncertainty and the stochasticity. Okay, so in terms of applications, so we are tackling with one is the open water system. I talked to Professor Koopman and some other researchers. One problem is the open water system. So you visited Singapore last December, from Marina Bay to Changi Airport, there will be a long island. And we'll control the water level within the island, between the island and the coastal area. So we will need to control the water level to mitigate the flooding. And uncertainties come from weather. So there will be big rainfall. It may be raining for 20 days. So these are big uncertainties to the system. And these are something we cannot handle at this point. Another example is about the carbon capture process, right? So we talked to the ship owner as well as the company stakeholder, whether they would be able to accommodate, for example, like make the operation of the diesel engine in a gentler way. It's impossible. This is what they shared. So which means that we will need to receive fluctuating flow rates in the flow gas as well as the concentration. The carbon, the CO2 concentration in the flow gas of a ship, depending on the operating condition, may fluctuate from 2% to 8%. And that is something we are dealing with, which means that the state value basically just vary from 1 to 4 or from 1 to 5. In terms of flow rates, it could be a multiplier of 10. So which means that the fluctuations are something we are not able to predict, but that is something we must deal with. So I would say stochasticity and uncertainty. Thank you.
Any other questions? Yes, please.
Yes, please.
Thank you for the talk. I think at some part of your presentation, page 66.
66.
You mentioned that you don't like update the new network parameters using incoming new data.
Yeah.
And could you elaborate more on the algorithms, how you update the parameters in your networks, and also the computation side?
I see. For the meta learning part, okay, to clarify, probably I just delivered inappropriately. We never update the neural network parameters online. For the meta learning framework, we update the Koopman matrices. We updated a matrix. So when we encounter a new operating condition, but that is more about adaptation. It's like a correction term. It's an innovation term, like a common filtering, right? So we updated a matrix without solving any optimization. And from here, indeed, we update the B matrix, C matrix, and the D matrix. We update most of the matrices within a Koopman model. But these are the outputs from additional neural networks. So we just make the training more complicated. But for online implementation, we will avoid the update of the neural networks. So that is the option for other applications. So it's just because of the special need from the funding agency, we will not be able to retrain the neural network. Yeah. Thank you.
Okay, so I think there may be a few more questions, but perhaps we can ask, close the seminar and sort of individually ask the speaker. But before we do it, let's thank the speaker one more time.
And thank you so much for taking the time and the valuable feedback and insights. Really appreciate that.
Anyway, I have the deadline next week afterwards, so you should, should we wait after? Maybe I will give them a
Yeah.
But just,
Yeah.
I wanted to ask a couple of questions. Yeah, please. Yeah. I think I will say that I will at least let it.
But maybe stop. There's nothing.